talking about subduction, and it's quite a huge topic, and I really can't cover even a quarter of it. And some of the people in this room are really experts on that. So this is a modern map. If you're going to study a planet, the way to do it, of course, is first send satellites around, map the surface, and then when you have some understanding of what you're doing, then you go down and you look at detail. Of course, we didn't do things that way. But finally, we're getting to that stage. And this is a satellite map of the Earth's topography. And it may be fairly intuitive that you can see topography of the continents, but you're also seeing details of the ocean floor right through the ocean. And that, I won't go into detail, but it's done using gravity and sea surface elevation. You say, how can you do that with all the waves? Well, the pixel size is 3 kilometers on a side, so it filters out all the small stuff. The continents are really different from the oceans, and they just look different on this map. That's because they are. The continents have had a really complex history. With the oceans, we can actually read their history from this map, see what has been going on. Not the time, but there is time data for that. The continents are made of different stuff. The basic rock type of the continents, the most common, is granite. Granitic rock made of quartz, feldspar, and other minor minerals. The oceans are made of basalt. It's mainly olivine and pyroxene. And a big difference is that quartz melts at a much lower temperature, which means that the continents are much weaker than the oceans. So that brings us to kind of the start of modern tectonics, modern in the last century. Alfred Wegener proposed that the continents drifted apart. And not only did he fit the continents, but he found that a lot of the geology fit nicely together when you put the continents together. We'll go into the details of that, but I think if you'd left it at that, the development of tectonics would have been different from what we've seen. But I think Wegener was pressed by people saying, how's that possible? What kind of mechanism could do this? Wegener didn't really know, and he said, well, it's sort of like ships going through water. You know, the continents are just moving through the ocean basins, which was quickly pointed out that this is an impossibility. The continents are actually much weaker than the oceans. So geologists looked at that and said, oh, continental drift has been disproven. We don't have to deal with that. But not everybody. In the mid-20s, Reginald Daly from Harvard published a book called Our Mobile Earth. And Daly knew a couple things. One is that the Earth's outer layers consisted of a lithosphere that was sort of rigid or elastic. And below that, what we call an asthenosphere, where the rocks could flow over geologic time. He didn't know what it was made of, and this isn't correct, but he did have an idea of what the upper layers were. He also knew that the Earth was shrinking. That was obvious because the Earth started hot, and you cool rocks and they're going to shrink. Everyone knows that. So the Earth must be shrinking. But he said it's probably not shrinking that quickly. And what it might do is just buckle the lithosphere. And where it buckles, you pile thick sediments. And at some point, the lithosphere might break, go down into the asthenosphere, buckle the sediments and make mountains, and pull apart someplace else and make ocean basins. Now, this is really forward thinking. Not too many people took him up on that. Turns out the Earth isn't shrinking. There's a lot of radioactive heating that people weren't really that aware of that keeps the Earth hot. And the process, which we'll get into of plate tectonics, is very efficient at cooling off the Earth. Another model to explain drift was an expanding Earth. And there were some very outspoken people, especially Warren Carey. But if you think about that a bit, it's not really a viable alternative. Arthur Holmes knew about the lithosphere and the asthenosphere. He said, well, if you have convection in the asthenosphere, it will pull apart the lithosphere where you can get new ocean forming, and where these convection currents come together, they go down in subduction, forming mountains and deeps. So that was a pretty forward-thinking model. In 1964, Bullard, Everett, and Smith gave a talk about fitting the continents together, not much different from Wegener, except that they used a computer to find the best fit. Well, geologists looked at that and said, oh, the computer did it, it must be true. So at that point, everyone thought continental drift was happening. But by this time, there was a lot more data to look at. Now, another really important observation was seismology. This is worldwide standardized seismic network that was started in about 1961. So this is about 6-7 years worth of earthquakes from that network. And it showed that most earthquakes happened along very narrow boundaries. And where you see these abundant dark zones of earthquakes, those are largely subduction zones where most of the big earthquakes occur. And along here, these very faint zones, no less important, that's where the oceans pull apart, make new crust. There are also these long faults, like the San Andreas. When I was an undergrad at Berkeley in 1962, nobody really knew why there were these long faults with big offsets. There were these funny explanations, but in 1965, J. Tuzo Wilson said these long faults are transform faults, which just means they're a boundary, laterally slipping boundary between two big plates. And so he drew this map. Now, in 1967, a couple of postdocs at Scripps, Dan McKenzie and Bob Parker, were looking at this paper. They also were looking at the earthquake map, and they knew that most deformation happened along narrow zones. They were very good mathematicians. And they said, aha, we can explain all of this by rotation about an axis. So they determined an axis of rotation between North America and the Pacific using two earthquakes, one in Central California, one in Alaska in the mid-60s. And those two gave them their rotation axis. And with that, they could predict the motion along the entire boundary between North America and the Pacific. Well, this is in the fall of '67. They quickly sent out a very short paper to friends at Nature, who quickly published it in December of '67, and they became the first people to talk about plate tectonics. At the same time, there was a very quiet, shy geophysicist at Lamont named Jason Morgan, who was quietly doing the same thing, but putting together all of the major plates around the Earth, finding their relative motions, predicting all of the relative motions. He submitted his paper to Journal of Geophysical Research, which is slow and ponderous and doesn't get whipped out. And that wasn't published until March of '68, but it was very clear that Jason Morgan was an equal originator of plate tectonics. Now, some really exciting data happened in the late 50s. This was a map put together by Raff and Mason, published in 61. And the Coast and Geodetic Survey had planned a bathymetric survey of the margin of Western North America. And they asked if they could come along, toss over a magnetometer, measure the magnetic field, and they said, sure. And this is what they found, this phenomenal striped pattern on the seafloor. And they had no idea what the reason was. But at the same time, there was a group, Coxtole, Dalrymple, and other groups that were working on the fact that the Earth's magnetic field reverses. This is from a big stack of volcanic rocks in Hawaii. And they found that rocks that are younger than 700,000 years are normally magnetized, normal being what the present Earth's field looks like. But from 700,000 to 2.5 million years ago, the rocks were reversely magnetized. So the North Pole is in the south with a couple of small events, normal events. And then from 2.5 to 3.5, normally magnetized with a small reversal and then reverse, etc. So they started to put together this time scale of magnetic reversals. Well, a bright young grad student in England, Fred Vine, took a look at that Raff-Mason pattern and he said, I can recognize the Cox-Dole time scale right here. This is the 700,000 year rocks. Over here is the negatively polarized with a couple of little positives. Here's the positive. So he was able to take that out to about 5 million years and then saw more stripes. And so he said, okay, this is the seafloor pulling apart. If it happened at the same rate, we can just predict the ages going out to 10 million years. Okay, well, this set off a flood of work. There's a lot of magnetic data throughout the oceans. People were working on that. 1968 was the start of the ocean drilling program, the deep sea drilling program that started in 1968 and has been going virtually continuously to the present day, drilling holes in the ocean all over the place, all the oceans, high, low, intermediate, and these are giving ages of the seafloor that you can match with a magnetic pattern. And the first map of the age of the oceans was in 1972 from Larson and Pittman. And for the most part, especially the little oceans, the youngest rocks are right in the middle of the ocean, and the oldest rocks are right at the edges. And that applies to the Indian Ocean. Doesn't apply to the Pacific. Here, the oldest is in the west and the youngest in the east, but there's subduction around most of the Pacific. And this pattern tells us about the evolution of the plates. Okay, so getting into subduction, this is now a more modern distribution of earthquakes. This is in South America, showing the earthquakes going down deep into the mantle in a couple of places. And the earthquakes are telling us where the plate is descending and how it's descending. So actually my interest in all of this has been right at the interface. So when I talk about subduction zones, I'm really talking about working on the interface, whereas there's a huge amount more to subduction zones than just the interface, but it's a pretty important part. And so people knew that this plate was going down into the mantle by subduction at the trenches. And Dave Scholl, Roland von Huhn, and co-workers ran some seismic profiles. And I'll talk a lot more about seismic profiles. But what they showed was that in the Chile Trench, there was this big pile of sediment, very flat sediment, seemed to just lap up against the rocks of South America. And they said, well, wait a minute. Plate tectonics tells us that these plates have to be coming together. But if they're coming together and all these sediments are just sitting flat, how can this be? And so they published this in Science magazine, 1968. That's when I was a grad student. So seismic reflection, it looks something like this. You have a ship, you tow a sound source behind the ship. The sound goes out, bounces off the bottom, sub-bottom layers, comes back to a listening device, and you see that data displayed on a recorder. So here's the outgoing signal, the seafloor, some deeper layer here, and undecipherable stuff down here, and then the sound bounces a few times, and here's one of the bounces. Well, in 1969, a group from Woods Hole ran a profile off of Barbados, and they said, well, that looks like sediments are being deformed. I mean, you're not seeing a lot of detail in this, but you know, the data is pretty raw. And I was doing my thesis off of Northern California and Southern Oregon. I found the same kind of thing that Scholl and von Huene did, but it looked to me like actually these sediments were deformed down into this ridge, and my interpretation looked like this, that are published in Science. And a lot of people thought, you know, this makes a lot of sense. Got a lot of pushback as well. So I went out a year or two later off of Washington and got this profile. And that to me looks really clear, that here's this layer that comes right up, it's folded. These deeper layers are here. Here's some layers that lap against, but they're actually folded up, they're pushed up along the side. So the data is still pretty rudimentary, but it's pretty clear that that's what's happening. You have deformation. And here's a sort of a cartoon analogy with a snow plow pushing up a bunch of deformed snow in front of the plow. Okay, but subduction zones are really complex, and the few examples I showed are really lucky examples. Took a lot of other data and couldn't see a thing. It's sort of like what Scholl and von Huene found. So the data needs to be processed through digital imaging. Here's an example. Here's a seismic line, and you see a bunch of diffractions over here. But when you process it, process called migration, then this becomes this nice irregular layer. So you can see things a lot more clearly. Here's an example we did off of Panama, showing really nice deformation as Panama is moving north. Okay, in 1973, there was a conference on subduction zones. The people who did the best seismic processing on the planet were oil company people. So this group from Exxon stood up after the rest of us gave our little talks, and they said, all right, this is what subduction really looks like. And so they showed this lithospheric slab going down based on the distribution of very poorly located earthquakes. They showed volcanics coming off the slab. They didn't see this, they just drew it. But they showed a big basin here, and that's what they were really interested in, Guatemala. But then they showed this big accretionary wedge going down to the trench. So everybody left and said, okay, that's what subduction looks like. Except a few years later, there was a drilling expedition into the Guatemala margin, and they drilled in a number of holes found no accretion, all old Mesozoic basement rocks, like the oldest rocks you see along the coast. So it looked like there was no accretion, completely opposite to what the Exxon guys drew. And in the late 90s, I was part of a cruise off Nicaragua, showed this big basin, this very intense reflection going right down to the trench. We didn't have drilling, but there were places where this layer came to the surface. And being an old-time marine geologist, I am really good at dredging rocks. And so we put over a dredge, pulled up a barrel full of old rocks. These were Mesozoic rocks, similar to what you find the oldest rocks on the coast, and similar to what they found off Guatemala. So that led to a new paradigm that said, okay, subduction zones are either accretionary or they're not. And if they're not, they actually may be erosional, where you're pulling material off and bringing it down deep into the earth. So some places the continent's growing, some places it's shrinking. And that was based on a study by Von Huene and Scholl. You've heard of them before. It's a little tricky to understand. Focus on this particular layer all the way down. That represents the present seafloor. So, and they had drill holes going down to it. They found unconformities, which meant times when that seafloor was at the surface being eroded and then subsided to where it is at present, sometimes as much as 5 kilometers. And so they said, we can quantify the amount of subduction erosion. If you measure the amount of subsidence that's caused by eroding off this material and the ground goes down. So now there's a new paradigm in town, but we still needed better imaging. So this is kind of an overview of a 3D seismic ship. And I had a cruise in 2011. So this is shown in schematic form. There's the ship. These 2 dots represent sound sources behind the ship. And these lines of squares going back are listening devices. We had 4 lines of listening devices, and they went back 6 kilometers behind the ship. And so each line had 468 separate recording channels. And there were 4 of them. And these X's are sort of data points, bounce points off the subsurface. So you have a sound source, a bounce, and it's recorded at one of those listening devices. Okay, so for every shot, you have 468 channels of data. Multiply that times 4. And each channel is about 10 seconds long. It's digitized every millisecond. So that's 1,000 bits of data times 468 times 4 for every shot. You shoot about every 10 seconds, and we were out there for over a month. So you can add up how much data. That's a huge amount of data. Wow. And all of that has to be processed. This is what a 6 kilometer long cable looks like on a spool, and somebody has to go through and make sure it's spooling on neatly. Very dirty job. Here's one of the sound sources. Compressed air goes into this chamber. Every 10 seconds it's released, goes out of those ports, makes a boom, and the source may be about a dozen of these things of different sizes. There's a reason for that. I won't go into now. So this is what the pattern looks like. Start over here, come around, make a loop to this line, come down here, to this line, etc. And we do that for a month. And every day we go down and look at the data, and it's like Groundhog Day. It looks the same as yesterday. Except this is unprocessed. Once processed, it's not really the same. The site we chose was based on a 2D seismic line shot by the German BGR. And we did that because we could see the downgoing interface going pretty far down. There was a significant earthquake that happened in the region of this interface. And we had proposed drilling a long hole to go down to that interface and try to understand the physical properties of the rocks where slip occurs and generates earthquakes. That still hasn't happened, but to do that, we needed 3D seismic. So we look at the 2D line, which is processed as well as anyone could process it. And then here's a 3D line in the same zone. This doesn't look exactly the same to me. Blowing that up, you can see a lot more detail that we can't see in the 2D. And it's a very different interpretation than the 2D. When we go upslope, we get to the outer shelf, see all these little faults that cut the sediments. And it's not possible to tell what orientation these faults are going. But wait, this is 3D. So we can cut a horizontal slice through the data because we can look at any orientation we want. And when we do that, we get something like this, and we can see all of these faults. And it's a very intricate intersecting pattern of faults. It'd be completely impossible to do with 2D seismic data. The other thing we could do is neural network analysis. And here we're looking at the probability of fluids coming through these rocks. And the high probability is shown in the green color, greens and blues. And for the most part, the high probability of fluids coming up are focused on fault zones, which one would expect. Oh, and at one point, we have a high resolution seismic line, very high frequency, that is showing, this is the seafloor, and then an acoustic plume that goes right to the surface. We weren't able to sample that, but from other data that we have all over the world, it's very likely methane. There's a lot of methane in continental margins, comes up, and as the earth warms and the ice in the Arctic and ice in the upper part of the continental margin melts, you have more and more methane coming up. Well, you don't have to look at 3D either vertically or horizontally. And here's the cross-section. My student Joel Edwards spent months digitizing the interface between the plates. And when we look down at that interface, here's the trench axis, you can see all of these big grooves going across the fault surface, and that's telling us the direction of movement of the fault. This isn't new kinds of stuff. Geologists have always known that if you see a fault in outcrop, there are often scratches along it, and they're called slicken sides, tells you how the fault moves. These are very large. They've been seen on extensional faults where the fault surface is exposed. Never on the thrust fault, because that surface is never exposed. There was also some drilling out here near and in the area of this 3D seismic line. And another thing that Joel Edwards did is he mapped a whole series of unconformities. These are layers that were at the surface, got eroded, and then subsided. Like this, you can see the layers are being truncated. And if you follow some of these others along, you can see some truncations. And we were able to date those truncations, those unconformities, because we had drilling data and 3D seismic to be able to extend that. So here's reconstructions of this area. Here's the present. The red is our 3D area. This is a big fracture zone called Panama Fracture Zone. It's got a huge escarpment facing east coming along. And 3 million years ago, that escarpment, if we project that by known plate motions, that escarpment would have gone by this 3D area and done a lot of damage, including lifting the area up, eroding, and then subsiding as it passed. There's another feature, the Capos Ridge, that 1 million years ago passed by and would have raised the area and then dropped it. There's signs of seamounts that have gone under. And so it looks like in this area, up and down motion isn't necessarily due to subduction erosion, but to the passage of these bathymetric features that go by. Now, one other kind of tool, this is something that was dominant when I was a grad student. They're called echo sounders, and sends out a big spherical wavefront, bounces off everything, sort of look like this. You may be able to get some idea of where the bottom is. Here is down in deeper water. You can see all these overlapping diffractions. So you don't see a lot of detail of the surface. But in the 80s, a new tool was developed called multi-beam, and that allowed data from small areas on the seafloor to come back. And so you were able to map much more detail, both bathymetry and backscatter, which means the amplitude of the signal coming back. The data that's taken is very wide when you're in deep water and gets much narrower when you get into shallow water. And nobody does this work on the continental shelves. It's way too shallow, way too expensive. It's never done, except if you have 3D data and you're running very close together lines anyway. And so this is what we found, and these dark light bands are, it's an erosion surface, and it's showing the front of different sedimentary layers. And these layers are actually folded in a broad fold, and you can see faults cutting through them like this and like that, in a pattern very similar to the horizontal slice I showed earlier. So you can see that pattern right up to the sea floor with this very detailed data. Okay, and then there again is another view of that plume, and all these yellow dots are areas on the seafloor that show signs of fluids that have come up. They're big pits where fluids came up, bubbles burst, left pits of various sizes. Okay, so kind of as a summary, 3D seismic showed imaging of the seafloor and seafloor structure that's not possible without 3D. We can map distribution of fluids in the sediments. We can estimate the amount of methane coming up, and we can image methane seeps. Older models suggested that subsidence meant tectonic erosion, but what we see in the 3D is that uplift seems to coincide with the passage of these different bathymetric features. You can also see these deep grooves in the fault surface that aren't possible without 3D. And the bathymetry as well, highly resolved bathymetry, is able to show abundant fluid pathways on the shelf. So as far as my career, when I started my thesis at Scripps, I purchased the first seismic reflection system that was operated by Scripps Institution of Oceanography. In that early data I showed, I took, that's from a system that I was able to purchase with the small grant that was given to my advisor, and he let me do what I wanted with it. So I wasn't a lot of money, but I was able to buy that system, pay for ship time, and pay my exorbitant salary at the time, which was $200 a month. And I used that a lot in my career. My last two funded cruises were 3D seismic studies. I talked about southern Costa Rica. Also, we had a study off eastern New Zealand that I didn't have time to show. Now NSF would like to stop funding academic 3D ships. They haven't done it yet. And for a very petty reason, it's just hugely expensive. And in fact, for any size 3D seismic to be funded, it sort of had to go in again and again, even though it gets great reviews, until NSF can find enough money to fund it. Also, the US program for scientific ocean drilling began when I was a grad student, has continued almost constantly until the present, will end in 2025. We don't know what will happen after that. The Japanese and Europeans still have some kind of program, but ours was really the bread and butter drilling. So I've been in marine geology through a golden era, and probably retired at a good time. All right, so I'll stop there and see if people have questions. Yep.
What is the source of the methane?
Well, it's biological material.
So it's been trapped by biological, and then the subduction just brings it down?
No, it's trapped in the sediments. And actually the upper couple hundred meters of sediment tends to be composed of a methane hydrate, sort of an ice. And below that ice, you have trapped free methane. So decaying organisms give rise to the methane. And when you have faults breaking the surface, the methane can get out. As global warming continues, that ice will start melting more and you get more methane. But it's a biological material.
Follow-up question. How are these layers produced that we see in this bathymetry that you're showing us? That must be something pretty big happening, to the
This thing?
Yeah.
Oh,
Yeah. So
they're just sedimentary layers. Under the shelf, they're kind of tilted up a bit and eroded, and there's a slight fold. Actually, we think that a seamount may have gone under this, because all along Costa Rica, we can see places where sediments are bowed up, where a seamount has just gone through. So, but that's exposed at the surface, and the dark and light are just the different materials that backscatter. Al?
With regard to methane, current interest, obviously, there's a lot of interest in methane. What portion of this naturally forming methane compared to what's released by humans?
By what?
Well, how much of that methane that you see that's been estimated in terms of volume, how does that compare to releases by humans and oil?
Oh, you mean greenhouse gas? The amount that humans release is significantly larger. But over time, as the permafrost melts at high latitudes, see, lots of these seeps coming up there. In the short run, methane is a really potent greenhouse gas. It just worsens the. Oh, sorry.
So we're sitting right on the edge of one of these plates. So, and yet the fault is, in the inland side of us. So are we sitting on stuff that was scraped off of the Pacific plate, or are we sitting on stuff that was the old North American plate?
We're actually on stuff that was the old North American plate, because San Andreas is inboard. And if you move us down 300 kilometers south, which is the slip on the San Andreas, it matches up these rocks, which are called the Selenium block, which has granite. You can see granite on the campus. That sort of goes down to the southern Sierras. But the San Andreas cut sliver of that, moved it up to where we are. So actually, when you go east of the San Andreas, then you get into material that was scraped off through the subduction.
I don't understand why, but accept it.
Well, California is formed of mainly, not including the San Andreas, 3 belts of rocks. There's the granitic rocks of the Sierra. Then there's this big basin, the Great Valley, which is a 4-arc basin. And then west of that is a big pile of deformed materials. And that's stuff that was scraped off and accreted over time. And then that pattern has gotten a little bit confused by the San Andreas coming through and taking what was down south and moving it up north.
There was subduction offshore, perhaps. And then that subduction moved north. And then you had the Central Valley.
Yeah, you had in the Mesozoic, which is when a lot of this originated, this was a subduction zone. So the granitic rocks were part of the volcanic arc. And then there's a 4-arc basin in front, and then the stuff accreted in front of that. So a typical, very large subduction zone. Jim.
I have 2 questions reflecting the standpoint of, I think you're in this, or these reflect the one or two things that I actually sort of know about everything you've told us about so richly. The first is, in accounts of the shifts to plate tectonics that I've read, the role of the military played a part. That is, Cold War mapping of the ocean floor by submarines, etc. Is there anything to that? You didn't talk about that.
I left out a great deal. I left out a great deal.
Well, anyway, the other is, I encountered the word subduction for the first time in that infamous New Yorker article about the subduction zone off the coast of Washington, Oregon, Washington, and Vancouver, and the disaster that was fairly confidently predicted. And we happened to be driving right along the Oregon coast when that article came out, and we saw these signs every now and then when the road would go down to sea level. There'd be a sign that would say tsunami evacuation route, and it would arrow pointing kind of sort of vaguely uphill and away from the Oregon. Totally ridiculous. Well, I guess my question is, what can you tell us about that subduction zone, which is really right nearby and actually menaces places we might go and places where our loved ones live?
Yeah, well, the first question about the Navy. The Navy did do a lot of work in the oceans and also has been very supportive of oceanographic institutions making ships available. So there is military data, but a lot of the data that was collected that I showed is from academic surveys that have been done. I mean, you know, everything adds to it. As far as the Cascadia subduction zone, and that's the first thing I talked about, showed deformation off Washington, Oregon. Yeah, we're pretty certain that about 300 years ago, there was about a magnitude 9 earthquake, generated a tsunami, and the time and day is known pretty well because it was recorded in Japan, and there were no other similar events that happened. And Japan kept very good records at that time, and so so we do know that there was that major event. And there's been a lot of study of that since then about the history of slip along that margin. So that has been going on for a long time. It did generate a tsunami. And if you were driving by in certain areas and the tsunami happened, it could ruin your whole day. And driving uphill away from it is exactly the right thing to do. The signs are yeah.
But is there any, in the article, they actually speculated in the caution about predictions based on older temporal projections, endochronological estimates and so on, that basically had the periodicity of earthquakes on this zone, which basically said we're overdue. You know, that it was happening every.
Well, I mean,
But I mean,
anything can be due or overdue. They could happen anytime. I mean, you need time to build up the elastic strain, but 300 years is a good length of time. Yeah, there've been a lot of studies. There's a group that has studied turbidites, which are big, large sediment flows that have come down at great speed off of the margin and deposited out in the basin. And by coring through those, they are able to see the timing. And they suggest that many of these are generated by large earthquakes. And so they can get some timing of the likely, some indication of the likely timing. Someone over here.
And I got a kind of basic question about plate tectonics.
Louder?
A basic question. You've got two adjoining plates, like I guess the Pacific plate and North American plate here. And so the pictures I used to see were kind of like for subduction, is one going under another. So this would be a velocity component where they're moving together. But then it's also slip, I guess it is, where they're moving, naturally, laterally. So how would you compare those? Like here, is the slip velocity way more than that? I think subduction velocity in our neighborhood and elsewhere, or are they comparable?
Where do I think of it? Let me see. Okay, well, I don't have a good slide to show, but so here's the Pacific plate, North America, and right over here there's a little plate. It's called the Wonderful plate, and that's subducting, and that's what we just talked about before, where we could have this great earthquake happening. Then the San Andreas is down here, and then south of San Andreas, you get to the Middle America Trench, and there's subduction going on. Well, this pattern has evolved over time. So if we back this out, maybe 30 million years ago, we find that these two little plates come together and were a bigger plate. And when we back it out past that, then there's this large plate subducting under all of Western North America. So that's the subduction zone. And then over time, once the Pacific plate hits North America, its relative motion is different. The Pacific is moving laterally relative to North America. So once these two plates come together, where they're together, there's lateral motion for like the center plates.
And that lateral motion is much faster than,
No, no, it's just
You
different
said it was
plates.
at the moment.
It's
That's-
different plates. So you've got Pacific, North America, and this wonderful plate. And when they were together, it was called the Farallon. The Farallon's going under. North America is moving this way relative to North America. But if they're not touching, then it's not having any effect. It's only where they touch that you have an effect. So when the Farallon plate is touching North America, it's going in to do subduction. When the Pacific plate touches, it's sliding laterally, and it gives you a strike slip. And the subduction is occurring on your side. So there's subduction here and subduction here. And that join is growing.
Are there models of further continental drift over very, very long time scales? Are we liable to end up fighting Asia?
Oh, are there models? Oh, you can model anything. Yeah. There's actually a quantitative limit to future prediction. Yeah. So you can predict whether it'll be this or that, but there's a problem with future prediction. I mean, if things are moving the way they are, and the big plates, things aren't going to suddenly change, but they can change. So will we crash up here? I mean, I can give you other examples of lots of crashes. That I've done a lot of work in the Western Pacific. It's full of crashes. There was some, oh, Gail.
So I'm stuck a little on the very last thing you said about the funding that will sustain your entire career next year. And given everything you just said and possible implications for disaster planning and something else, that the data is generated by the kind of work you've been doing, what kind of debate is going on about discontinuing funding this kind of basic research? And what's the back talk from scientists about the reasons to continue?
Well, I mean, as far as 3D seismic data, they haven't stopped it yet, but again, it's just so expensive. NSF just has a hard time doing it. As far as the drilling, which has contributed so much to our understanding of paleoclimates, probably Jim Zakos is the person to ask, as far as the future of drilling and where we are now. No?
Well, I can say it's looking kind of bleak. NSF's budgets are getting tighter. The ring is expensive. The US is fairly a large part of the budgeting. I think that's part of the problem. So, I mean, the programs were always going to be finite, right? It's a question of priorities and stuff. But you're right. I mean, we're still working on climate issues that require ground truthing models using case studies from the past. And so the need is there. It's just finding money.
Is there a push and pull between the corporations who might be doing this kind of research and not wanting to use those resources for more sustainable future?
There's always been a lot of oil industry has always been lacking some of the types of data that they use. There has been sort of collaborative work between industry climate change, it's harder. Corporations that would, their foundations, but they don't have that. US is spending $70 million a year last year to support the scientific building.
Yeah,
Yeah, there's a big difference as to how subduction happens when you have ice, for example, the North Pole retreat, rather than water, or that makes no difference at all because of the motion of the rock system.
yeah, I'm trying to think of a place where there's subduction and ice.
Like North
But
Pole,
it shouldn't, I mean, the plates are so huge compared to the ice.
well, that's what it's meant for pole, for North Pole, Alaska, meets the Asia, and then you have the whole Pacific plate pushing up there. But that whole upper region is made of ice, not just normal water. Does that make a difference in the pressure of any kind? No.
No.
I don't think so, but you know, there may be, I mean, there may be some small effects, but that's a good question. I mean, the fact that there's no subduction in ice, you know, going under ice that I'm aware of, means we don't have a modern example. No, nice question. Any other, or have we done? All right, one more.
We're talking about the sources of information that you've been relying on. Are there new sources of information coming online, satellite imaging, and other things that may be replacing some of the stuff you've been looking at?
Well, there's a lot of new data. I mean, satellite, even better. I mean, one kind of study I was involved in is GPS, so we can actually look at really small motions in the plates, very interesting. And radar data that can show movements between the plates. So it's huge amount. Can't do the kind of seismic things on it. It's really important for understanding. There is a lot of other kinds of data. As I said, I haven't barely scratched the surface.
So Eli, we can say once again, we have a lot of food for starving America.